So I have calculator written here, not because most of it you need your calculator, but there might be some places that when we're calculating our inflection points and plugging it back into the original value, it might be hard to do without our calculator. We'll try to do as much as we can without our calculator. So f prime of x, well, that's easy. We've got 4x cubed minus 4x. And if we make that equal to 0, we could factor out a 4x. And once this factors, it breaks up into 3 places. So we got x equals 0, x equals -1, and x equals 1 as stationary points. Find out what kind they are. We can put them on our number line. And again, when I'm plugging in values here, we'd use our factored thing because it's easiest to do that mental math to figure out whether or not overall it's positive or if it's negative. So if I plug in a big negative number, I hope you can see that this will be negative, and that'll be negative, which 3 negatives all multiplied by each other will be negative, and this part would be going down. Between -1 and 0, if we try 0.5, well, negative 0.5, this is still negative, this is now positive, and this is negative. All those together make that section positive. 0.5, only the last one's going to be negative, the other ones are positive, and anything bigger than 1, they're all positive again. So we know that -1 and 1, those are local minimums. And 0 will be a local maximum. So we got a local min, a local max, and another local min. Plugging these values back into our original equation, we wouldn't need a calculator for. So we're going to get 1 minus 2 for both of those ones, and plugging in 0, you get 0, 0. I'm going to move back up and look at my second derivative now. Setting that equal to 0. You could try to factor this. Probably the best way is to move the 4 over and divide by 12, x squared by itself, which is the same as 1/3 equals x squared. So x is equal to plus or minus the square root of 1/3. So if you're going to make if you're checking your stuff there, did you remember the plus or minus? Then we make our number line to check our concavity. We've got negative square root of 1/3 and positive square root of 1/3. So if we try 0, you're going to get a negative. Start off with an easy value. If you would try a large number, it's going to be positive. Or a large negative number when squared will be positive as well. So we know that both of those are inflection points. And this might be where you might want to put them into your calculator, although it's not too bad. Did anyone do it without their calculator? What'd you get? Sorry? -5/9 for both? So it's just a matter of, can you take a square root like this to the power 4? It's not too bad because when you have 4 of them, 2 square roots are going to cancel out with each other. So you'll just get 1/3 times 1/3 and get 1/9 there, right? And then here you'll get 1/3. So 1/9 minus 2/3. And then -5/9. Everybody else get -5/9? Awesome. So When we go to sketch our graph, we've got some points on here. We know we've got 0, 0 as a local max. -1, -1, and 1, -1 as our local mins. We can put our inflection points on and estimate where they would be. Label them as well. This one would be the positive 1/3, -5/9, and this one would be our negative square root of 1/3, -5/9. Okay. Looking at our original function, could you factor that? Just going to see. We've already got our y-intercept because it happened to be part of our local, it's our local max. It's also one of our x-intercepts. If we look back at our original equation, I'll just write it over here. It was x to the 4 minus 2x squared. If you factored out an x squared, you would get x squared minus 2. If you split it here, you can see x equals 0, which we already know was one of our points. But here, you'll get x equal to plus or minus the square root of 2. So if we wanted to put our x-intercepts on here as well, we would have root 2 comma 0 and negative root 2 comma 0. And when we go to draw our final graph, this part is concave up, this section is concave down, and this section is concave up again. We have a real accurate graph.